So the derivative with respect to that variable would just be the variable y, so you'd multiply it by y. Okay. Just give me a quick thumbs up if everybody's okay with that. Okay, excellent. All right, so if you're still a little fuzzy on that, just stay after class so we can work with you on that one. But it's straightforward. My main interest is to just do these skills. I'm not going to ask you to prove anything about them, but you should be able to compute the partial derivatives and have an understanding of what they basically mean. And this partial derivative formula is a formula that you would plug x and y into to get a number, which would tell you how fast that function is changing with respect to the x variable. Likewise, if I take the partial with respect to y, in this particular case, it's again going to be a cosine of x, y, because the y variable is the one that's being differentiated. It's the one that's changing. Everything else is thought of as a constant. So when you compute the derivative on the inside, that's just going to give you the x variable. And so this would be the function that we were thinking about. If I was going to compute a second derivative, we just do x twice. And if you had something like this, remember, you do this one first, and then that one's called a mixed partial derivative. Some very beautiful properties that come out in physics applications from this. That's basically what I wanted you to understand in that context, okay? Another thing I wanted you to be able to understand is that differentiation is just an expression of the fact that a function is proportional, or a function's output is proportional to small changes in its input. So if you just think of something like an ordinary function of one variable, and I ask you to think about what df means, that means the change in f when you change the input value, so that change is going to be proportional to the small change in the value of x. A function which has that quality is said to be differentiable. Other functions don't. But if the function is that way, you also hear the term smooth for that. You could run your finger along the curve, you wouldn't feel any sharp edges of that. So another way of saying the same thing is if I write something like this, and that's going to be equal to the original function plus some constant, we call that k1 times dx. This is the proportionality constant. The behavior of the function is going to act in this way. And that proportionality constant will turn out to be the partial derivative, or the actual derivative or the partial derivative as a function of two variables. So the value of k1 is what we mean by that derivative. It is the proportionality constant at that local place. So you could actually think of it from that way. And I can write it this way. Of course, this is part of the explanation for the expansion of the Taylor series. But it's this quality of functions that we ultimately assume in physical applications. We assume our functions aren't strange, that they're normal kind of functions that follow these laws, follow the equivalent, supposedly, of atomic hypothesis. Interestingly enough, classical physics assumes atomic hypothesis, even though it's not, sorry, the atomic hypothesis is not correct. It's only later on we switch over to quantum physics. So I want you to sort of understand that. Also, if you consider a simple function like this, if I write f of x equals x squared, in a moment, let's student in. And that can be, of course, graphed as a parabola. And if you draw a tangent line at any particular point, let's say right here, then the function is going to look like a line that you kind of magnify into it. And that is that the proportionality constant, this k here, is going to be some value. Now, it's going to be bigger here. You switch to location, but if you don't move too far from any individual point, that proportionality constant is a good approximation. Notice this would be bigger here, smaller here, still positive. If I pick the point here, it's going to be negative, and of course here it's 0. You know, if the derivative of a function is 0, it means you had a local minimum or a local maximum. Okay, so kind of keep that in mind. If you think about a function like this, though, the absolute value of x, its graph looks like this. It's this very sharp peak. And no matter how much you magnify this, it'll always remain sharp. Because if you look at this in the high and higher magnification, it's still going to look like a sharp peak. Whereas if you magnify this, it starts to gradually outcome a line. Same thing here. If you magnify this over and over and over again, it starts to behave more and more like a line, like a linear expression. And to be differentiable means that it's locally approximatable by a line or by a linear function. In the 2- and 3-dimensional cases, instead of using a tangent line, we use a tangent plane or a tangent hyperplane for higher dimensional situations. And places you'll see that classically in classical physics predominantly, by the way, will be in thermodynamic studies and other places of that nature. So you should have some experience and exposure to it. That's the only reason I'm doing this. Now, if you think about a function of two variables, I ask the question, what if I change the input value just a little bit, dx, and I change input to y, dy, how will that change the total value of the function? Well, that's going to be equal to the original value before the changes, plus whatever proportional changes are there. So we think of this as k1 dx plus k2 dy. So this represents the small changes in x. This is the proportionality constant, and that's what you add to make the corrections to what you originally had to get the new values of x. And these, of course, will be the partial derivatives, so I can write this way. Here I'm going to use a partial derivative with respect to x, dx. And that's what I want you to think about. This is just a proportionality constant. You can think about it in that way. It's a number. It's just a number, like Grandpa Greg used to say, that you would get if you applied in the local coordinates. Actually, this really should be an x and y. We just don't write it. Same thing here, just that the partial derivative with respect to y. So that's what I kind of want to train you a little bit to see this. When you see these expressions, you're thinking proportionality constant. Everything boils down to that simple idea. The mathematics is just being more precise in a particular case. And I cannot tell you how much progress you'll be able to make in your development education if you embrace that idea and think about it. You got to kind of keep working on it, because sometimes you kind of lose a little bit, come back to the gain some more ideas behind that. So this is one of the things we were talking about last time. In fact, if I take this expression and bring it over to the left-hand side, just complete this here, what I'm going to get is the change, or you're going to get the new value of this function after the change, minus what you started with, is equal to these expressions. And all of this just becomes df. What we're saying is that df is equal to this. Okay. And so I want you guys to understand this, that df represents the change in the value of a function at a point. If you move a little bit away from the point, that's what that dx is saying. That's what this dy is saying. These are little small changes. They're not infinitesimal. They can be made smaller and smaller, but they're not in fact basically infinitesimal, which is small, like 0.1, 0.2, or 0.01. These just represent how quickly the function is changing. So give me a quick thumbs up if everybody understands it's okay with this expression here. Shane.
Professor, I don't know if it's your mic, but every time you talk, there's just
give me
a
one
lot
second. I gotta turn my down. Hold on a second. Hold on, Shane. Give me one second. I gotta switch out here.
Yep. All right.
Okay, Shane, go ahead.
I don't know if it's like just your mic, but every time you talk, there's just a lot of background noise. So I don't know.
Can you hear me okay? I know there's some background noise from this air conditioning system here.
It's almost like an echo reverb when you talk.
You hear me now okay?
Yeah, that's a little better.
Okay, all right. That'll be better. Okay, let me go back. All right, should be better now. You hear me okay? All right, so this expression here is something I want you to understand. Now, we can take this one step further, interestingly enough. If you think of these, remember, they're just numbers. We can actually represent them like a vector. We can think of this as partial of f respect to x, comma, partial of f with respect to y, comma, dot dx dy. Because we can rewrite, this expression here, if you dot this again, after all, partial of f with respect to x dot x is this plus that. So this is sometimes referred to as the gradient vector, which describes the rate at which a scalar field is changing in some fashion. So these quantities themselves can be viewed as vectors in that context, or in a more general sense as an in the product space. Okay, so make sure you have an understanding of that. We're going to exploit that. Let's also go back. Something else we talked about. Now imagine an XY coordinate system, and you pick a point here. Point here. If I call that X and Y, and I make a small change, I'm making this big so you can see it. Let's imagine this is dx, a change in the value of X. This is dy, change in the value of Y. And if I do those changes and I added them to X and Y, I would get the point X plus dx, Y plus dy. And so therefore, if we draw this little triangle, the sides of these things is dx, dy. So therefore, this is just going to be square root of x squared plus dy squared. And this is usually referred to as ds. And because it does satisfy the Pythagorean theorem, we can write ds squared, this is for spatial distance, is equal to dx squared plus dy squared. Everybody okay with that? All right. Now, one thing I want you guys to study, this one thing I'd like you to look at, kind of zero in on for the exam purposes, one as a test topic, is I can rewrite this in another form. It's equivalent, just one you may not think about, but it's a generalization. And these ideas are due to your great Professor Gauss, and his student Riemann, who's also one of the great professors, just one less grade on that one. And so remember what I said last time, I could think of this as 1 ds dx dx. So I can write dx squared this way. And strange, I want to add in this additional zero piece. And I can always do that because anything times zero doesn't change it, but I want to have it that way so it's in a specific format. Plus dy dy. Everybody all right with that? Now, the reason I want to do this is I can then recast this in that this general Pythagorean theorem expression can be thought of as a special case where I just put ones in front of this and one in front of this where these zeros don't count. But if I draw pictures on a surface, like a sphere or a football or some other curved shape, then there will be numbers here that correspond to the fact that the thing you're drawing on is no longer a flat surface. That is, the fact that if you do geometry or drawings on things that are not flat, then these numbers will change. In the case of a flat surface, they're always 1 and 1 everywhere. But you have to remember that these will change if you're at a different position. So for example, if you were drawing something on the surface of a football, imagine like a shape like this, basically an ellipsoid, okay? If you drew curves here towards the pointy end versus curves over here, then these numbers are going to change as you move around. On flat surface, they're the same. On the surface of a sphere, they're the same, they're constant, which is that they're no longer this 1, 1, 0, 0, 1 pattern. In fact, knowing these numbers at every point in the space, every point in the surface, will allow you to determine the geometry of the surface and its geometric features. And these numbers collectively are known as the metric tensor. And the term metric here basically means the measurement between, in this context, means the formula tells you the distance between 2 points that are close to each other. You assume that they can be made so close that any errors can be as small as possible. Now I can generalize this a little further in the sense, instead of using x's and y's, I want to use the classical contravariant notation. This is a little strange when you first time see it, so I want to understand it. So I can rewrite this as dx1 dx2. Now, these do not mean squares. What they mean is literally, instead of using subscripts, we're using superscripts. This is one of the big innovations by Chiba and a couple other early workers in this field shortly after Riemann did this particular material. And I wanted you to have an understanding of that. Okay? So all we're doing is doing a change in notation here. And instead of calling this a 1, I'm going to call this G11. And 1 and 1 corresponds, actually not 1, 2. So this is the 1 here in this particular case. So the 1 here means that dx. dx2 would correspond to y. But this number here is usually written by the variable G11. And the numbers here correspond to the superscripts you see here. This would be G12 dx1 dx2. So the dx1 corresponds to dx, the dx2 corresponds to dy. You can kind of see partially why I want to do this. If I use this notation, then I could have dx3, x4, so I can have an arbitrary number of dimensions. But by having superscript and subscript notations, I can allow for more generalized coordinate systems. And that's exactly what we need when we start talking about more advanced perspectives here. Now, what you'll see is the stuff you've been taught is just a special case of this broader point of view. And it takes a little time to see it. That's why I want you to understand it. Let me write this now as G21. This would be dx2, dx1, and because you have a dx2 corresponds to dy, and dx2, and that's how they're written, correspond to dx. And the last one would be G22, dx2, dx2. And this expression that you see here would literally be a product of numbers. It's going to be some number times that small amount of dx. It could be something like 0.1, this could be 0.2. There's another number called G12, be multiplied by again 0.1, 3. I'm sorry, this would be the same if that was the case. But it's just a product, literally just a multiplication of these numbers. Because it's a sum like this, we can rewrite it in a double sum notation. We have j equal to 1 to 2. And I is equal to 1 to 2 here. Obviously, this can be made 1 to 3, 1 to 4 for higher dimensional things. And if I'm trying to stay in 2 dimensions, we can get some insights. And this would be Gij dxi dxj. And notice how you have superscripts here with subscripts, and that's done intentionally. And the idea is that when you see expressions with a superscript and a subscript in the same form, it means that there's a sum going on. There's an implied summation here. Now, it turns out that Einstein actually studied this particular work for a number of years. In fact, he worked at Gauss's Riemann University, which was Göttingen University, one of the lead centers of mathematics in the late 1800s, early in the 1900s. And he studied with professors there, in particular one professor, Minkowski, who became later on, who was able to understand his work a little deeper. He understood it physically. He didn't understand it mathematically. And that's the reason why I could go there to kind of work with these professors to sort of have a deeper understanding of it. Because he was working with expressionists very commonly, he kept noticing that every time he did this, he always had this situation where he had this lower indices and upper indices, and always had these summations here. And he realized I can sort of drop this as a shortcut because I know I'm always going to be adding them anyway. And so this came to be adopted as the Einstein summation convention. And what I'd like you to know for your test is that convention. So you should know this. And you don't have to prove anything. I just want you to be able to explain to me what it is. I would ask you a question. What is the Einstein summation convention? Give me an example. This is a good example, okay? And so literally what you would write is just this. And without the summation. Interestingly enough, so useful this idea that Einstein wrote a letter with his friend who was, so I discovered a great thing in mathematics. It wasn't so much a great thing, which is it was a very convenient notation. And it was so convenient, not only did it work with his field, but a lot of other fields as well. So when you continue on your studies, you're going to see this more and more often. And so here's a good place to actually study in the place he did it. So when I write something like this, it means the same thing. And what you're supposed to do, you just use this right here, which represents just one piece of this larger expression. If you really multiply this all out, it can be all these little things here, but it's convenient just to write it this way with this summation implied. And so this is the famous metric tensor, which basically allows you how to find distances between your points. And it will turn out that this Gij is the tensor itself. This is sort of the tensor product form. Actually, the whole thing's a tensor, but it's multiplied together. But it's this Gij's that I want you to understand. Okay? Last time I also told you that you can rewrite this expression in the following way: dx1, dx2. And you think of this like a matrix. You also hear the term quadratic form. All of these are the same notation. This one's a little easier to see. And here you see the metric form for this, okay? Now, one thing I haven't emphasized here is that these Gij's change as you go from point to point. We're assuming you're at one place, and then you're looking at the environment around you. If you move to another place, you got to look these have to be updated. So you can imagine, for example, that football I was talking about. So if you had this football shape like this, let's say you were a small little bug and you could live on this football shape, you could go to each point and you could draw lines on it. And remember, lines are the shortest of the 2 points, but each point would have a set of these things. So you have to imagine a matrix. And the only difference between a matrix.
Sorry, Professor, real quick, can you move down the paper so we can see what you're writing? Thank you.
So the only difference between a matrix and a tensor, okay, is a matrix is just a set of numbers. A tensor is one that changes in a particular way, and it's that particular way that I want to show you the formal definition. There are other definitions as well that are all equivalent, but this is the classic one that was originally done by Gauss, Riemann, Lebedev, particularly Lebedev and Einstein. So at each point, you have to imagine a matrix that tells you how to measure small distances. So there'll be one here, there'll be another matrix here. I'm just making up these numbers. You got to imagine for every spot, there's a matrix. So you can imagine like putting a pencil there, a matrix would pop up. Just like you can imagine a vector field where vectors associated with each point. You can assign what's called a tensor field to each point as well. So this again is a generalization of a vector field. So we talked about vector fields in the case of sort of gravitation. I'll talk about more later on. You can also imagine the idea that every spot you go to, there's a collection of numbers like this that could be used in this formulation either this way or this way. And the totality of all those matrices or tensors is called a tensor field. And one of the big upshots of this is that if you know what those these values are, you can answer all the questions about geometry on that surface. That is, if you lived on that surface and imagine things moving in these curved lines, that can be computed. Now, part of why we're interested in doing this is we study gravitation, particularly more advanced theory of gravitation, is that ultimately it will turn out that gravitation is a manifestation of curved geometric space-time. You need to see some of the elements there to understand how that works, and it's one of the great achievements of physics. And that's one of the reasons I'm showing you these details. But in principle, if you knew what these metric tensor values are, you can find everything there is to find about the surface, whether it's in 2 dimensions, like in these cases, or as we'll see in 4 dimensions when we talk about curved space-time in 4 and 5 dimensions. And that's why you need to have some experience with this, okay? Now, the way you would practically find this, by the way, is you could imagine going to one point and then making small little changes like 0.1, 0.2. And what you would do is literally physically with a ruler, and make it a little bigger here. Let's say at this point here, and you make some small little changes like this. That is, you add to this point here the value of like 0.1 to 0.05. And then what you do is you'd measure this with a tape measure, and you'd measure this. Okay? That is, you would know what the distance is from these 2 points along with this and this. Because if you knew that, remember this is a ds here, and we call it ds1 for one measurement. So this is going to be equal to g11, again, dx1, dx1. And that would be this number here. So this would be 0.1 here, 0.1 here, plus g12 dx, and dx2, etc. So you put the 0.1 in here, put the 0.05 in here, and you do that for all 4 of these things, and you get an equation. You also know this variable too. You get an equation in 4 variables. So you have to take 4 measurements in different directions, plug it into that expression, and solve the 4x4 linear system. You know what you guys are thinking? You can't wait to do that on the exam. I'm not going to make you do that. I just want you to understand how it could be done. And it can be done experimentally. That is, you just have to go to each point, pick 4 independent directions, or little small dx's and dy's, essentially, and then do that 4 times, then plug it in to this 4x4 system. Let me just show you a little more what it would look like. It's going to be g21, dx2, dx1. Remember what you would plug in for dx2, that would just be the 0.5 in this case, dx1 would be 0.1, and then lastly, g22, dx2, dx2. So everywhere you see a dx1, you replace with 0.1 for this example. Everywhere you see a dx2, you replace with 0.5. And of course, you're assuming that you actually measure the distance directly. That's where you get this ds2. And that gives you a single equation in 4 variables, what the metric coefficients are. You have to do that 4 times, create a 4x4 system, solve that system, and Mathematica will do that for you. Or modern MATLAB will do that for you. And then, of course, you have to move to a new point and do it again. And so imagine you do this procedure where you go everywhere in the space, but if you did that, then you'd be able to determine what the entire tensor field is. That's the perspective that Einstein's doing. Okay? And as we'll see with more, we show the classical, we show the non-classical version of that. So I want you to have an understanding of that. Okay, so certainly want to know what the Einstein summation convention is. Have some understanding of how this would work. How would you experimentally do this? Like, for example, one of the questions asked, is our own space curved? Could we find that out? And the answer is yes. There's specific experiments that we can do. Why is it so interesting to us? Because that means that the theory is testable. I mean, Einstein makes these claims. How will we know if they're right? We can actually try them out. There's certain predictions, certain things should happen. We can try it and see if that works. So I'm not saying it's easy. I'm just saying it's doable, that it's within human powers. It's not like, going to the other side of the universe or something like that. We could do that right here. It just might be tedious, a little bit hard, but it's doable in that sense, okay? So bear that in mind. So I said before, Gauss originally was one who started this field, and it basically, the mathematics of this is referred to as differential geometry. And it turns out it not only works for classical gravitation, but also other areas as well, in terms of dynamics and also just in quantum mechanics. So you should have some experience with this. Just give you a little history of this. In 1827, Gauss writes a very famous treatise. He does a couple of these, by the way, available on the internet. If you get a chance, I'll try to post them. Where he basically asks the questions about curved surfaces and how they can sort of be thought of as being embedded in higher dimensional space, So if you could think about something like this, imagine a hill. I've talked about this before. Imagine a hill like this. A hill has this rough kind of shape. Then imagine drawing grid lines now, like a football grid lines or a coordinate graph like that. And then imagine now doing geometry. What we're used to thinking is straight, 9-degree grid lines, but on a curved surface, they wouldn't be that way. They'd be at angles to one another, they'd be curved. And so the question is, how do you do geometry in that particular way? And that is what he was trying to address. And so his point of view and his approach was to recognize that this surface here can be thought of as a 2-dimensional environment, because if you're living on the surface and you want to describe another place, it only takes 2 numbers if you remain on the surface, with respect to classical grid dress. But this thing is also sort of embedded in a larger 3-dimensional space. So we thought that you should be able to view this as being embedded that way and then reverse that idea. You don't need to, but a 3-dimensional space. But originally his study was on study of mapping hills. He was actually assigned an assignment to do that by the Hanoverian government. And in the process of doing these surveying measurements, he came up with this. And he only did it for the two-dimensional case embedded in the 3-dimensional space. His student Riemann in 1854, I think I mentioned this last time, was given an assignment to do, he was required to give a lecture as part of his acceptance for the University as a young professor. So this was a classical tradition. Because it was a formal work, he not only had to make the proposal, he had to get it approved by the department chair. And as I said before, the customary usual situation would happen is a student proposed 3 topics. Usually the first topic is the one that I want to do. The department chair would usually accept that. Gauss though chose the 3rd topic. And the reason why, unbeknownst to Riemann, is he'd worked on this 30 years earlier, and it was a revolution. But he hadn't published it widely, so he was kind of wanting to see what Riemann would do with that. And so Riemann actually was a little bit concerned about that. We know that because he wrote letters to his father saying, Gauss has done this for a long, long time, and so I better do a good job. Because it was a formal presentation, it was actually written down, you should read it. And because it was intended to be for a non-specialized audience, it's actually readable. It's not super duper technical. You can actually understand it. It's kind of interesting because Rigid was trying to consider this and realized it was a generalization of what Gauss did. In the same manner that a 2-dimensional surface can sit inside of a 3-dimensional space, you can imagine a 3-dimensional space, curved one, sitting inside a classical Euclidean 4-dimensional space. That sounds kind of amazing. And you can also even generalize this further. You can imagine a 4-dimensional space sitting inside of a 5 or even higher dimensional space. And this is actually further generalized by a very famous mathematician called John Nash. They made a movie about him, A Beautiful Mind. where this was one of the things he did as a young man that ultimately was able to apply to economics. That is, the behavior of economic systems has the same geometric structure as a high-dimensional space-time. Unfortunately, he suffered some schizophrenia and couldn't quite publish as well as he could. But later on, the Nobel Committee recognized the quality of the work. And that work that you're seeing here is actually a manifestation of that. And complement to that is the famous Nash embedding theorem, which basically says that a curved space can always be thought of as a thing embedded in Euclidean space. Remember, Euclidean space is where there's no curvature. That is, when you talk about curve, you got to measure it with respect to what? And it's a little hard to visualize that. Just to give you a sense of what a higher dimensional space might look like, let's think of something like this. If I think about just a simple unit circle, you all know that is the equation for a circle of radius 1, right? So just in classical notation, we'll just do that. What would be the next level of that? Well, that would be a sphere that sits in a three-dimensional space. But what is the equation of that? It's going to be x squared plus y squared plus z squared equals 1. You can make it r for non-universal. But the point is, this sphere can be thought of as a subset of the collection of all points you can make using x, y coordinates. So this sphere is a subset of all the points in R3. And yet, locally, it is two-dimensional. You can actually, and if you pick this at random any two values, you can plug it in and find other decent values. So you can actually get the points of this in three-dimensional space. How would we extend that? Just add on another variable. That's typically done in that case. By the way, this is called the two-sphere, because it is two-dimensional sitting in a three-dimensional space. If we extended this, what's customary usually the x squared plus y squared plus z squared plus w squared equals 1. This would be the three-sphere. So this would be a sphere, dimension 3, this expression here, sitting in a four-dimensional environment, because it takes 4 numbers to describe the coordinates. Right? If I want to further generalize, as we did, we just we kind of run out of letters. So now we start using what's called the Cantor-Variant notation. So the x1 squared, remember this does not mean a power, it means variable 1, plus x2 squared plus x3 squared dot up to xn equals 1. So this would be an n-dimensional sphere sitting in a n plus 1 dimensional Euclidean space. And this is sort of the genesis of the things you'll be encountering as you use your career. Now, I mentioned a couple of amazing things that Gauss had discovered in looking at these environments of higher geometry. He kind of focused just on the surfaces of spheres, or surfaces in three-dimensional space. And so remember that if you think in classical Euclidean geometry, if you have a triangle like this, right, you know that the area of the angle is added to 180 degrees. And the proof of that is if you just extend this line here, and think of this as a point not on this line, there's one parallel line to every line here, right? It's the famous fifth postulate of Euclid. If you extend these two lines, one here and one here, then this line here can be viewed as a transversal across these two parallel lines. And so the moral of this is that this angle matches this angle because they're alternate angles. Likewise, this angle here matches this angle here because they're also alternate angles. So this plus this adds up to 180 degrees everywhere on a flat surface. Okay? But if you draw figures on a sphere, let's say it's a uniform sphere, then you can get a different situation. For example, last time I mentioned, you could take a triangle like this. Each of these would have 3 angles, right angles in them, so the sum is greater than 180 degrees. In fact, every triangle will have that characteristic. Now that gets closer and closer to 180, you get smaller and smaller, but that's because then what you're looking at is something that approximates that surface. But the point is it's always greater than 180, and this is what's called a positively curved two-dimensional space. If you think about a negatively curved space, kind of has a classic shape like a saddle, like this. You imagine like a horse saddle here. And the lines in this space, remember the lines you would get by connecting points together along the shortest distance. One way of sort of achieving that is imagine like taking these surfaces, putting them up in space and making them metallic, and then run a painted marble on them. The idea behind this is that they're going to move along the shortest path. So if you pick a line like this, and you pick a point here, and you put your marble here, then the paths might be something like this or something like this. These would be two separate lines passing through this point, and yet it's parallel to this line here because it never intersects it. You're used to thinking of lines as being straight. That's not the key thing. The lines that be the shortest distance between 2 points if you go between each point. In this case here, there are no parallel lines. They all will intersect. And so Gauss was able to show that here the triangles, well, the angle will always add up to something bigger than 180. Here they'll always add up to something less than 180. This represents the case right in the middle. We also hear the terminology. This corresponds to flat space, flat two-dimensional space, curved two-dimensional space, positive curve, this would be negative curve. And so Gauss's study in two-dimensional space can be visualized. The higher ones are much tougher because you got to use mathematics if you want to do that. But it's a straightforward extension, a generalization of what Gauss was trying to do. Now let me show you a little more of the tools that Gauss started with, although he didn't develop this as much as a couple of the workers a little later on did. And these are the definitions. They're called the contravariant covariant formulation. So let me consider this. We draw a vector in standard XY graphs. We call this the I vector that you're familiar with. This is also the J vector that you're familiar with. This is vector V. Remember, I can always express this as so many i's plus so many j's. Let's suppose that this is just 2i plus 3j. You've all seen something like that. Now, one of the reasons why we use this ij notation is because what we want to be able to do is express everything in vector operations in terms of dot products. Because if we can do that, then some very nice results follow. So you know that if I computed I dot v, I hat dot v, that's the same as I hat dotted with 2i plus 3j, which in turn can be distributed. So this gives me 2i dot I plus 3i dot j. But this is going to go to 0 because these two are right angles to one another. This goes to 1. And so you're just left with 2. So if I dot an I with a v, any vector, the resulting number will be the projection along the x-axis. Very straightforward, right? Likewise, if I dot this vector j, I get j, 2i plus 3j. And that's just going to be 2j dot I plus 3j dot j. And again, these will be at right angles, so they'll cross out. This will give me 1, and this will give me a value of 3. So dotting with this vector I gives, with the ordinary vector with I, gives me the projection along the x-axis. This gives me projection along the v-axis, the other axis in Cartesian coordinates. Here's the new feature. In general, this won't work. It only works in the very special case that everything is perfectly at right angles, everything is unit scale and all that. In general, what you're going to have something called skew coordinates. Imagine having something like this. The vector I'm going to call E1 with an upper index. Another vector E2. And this is very common in textbooks that these I'm showing it to you. Okay? Now, so we have the same vector we had here. So I'm just doing the same thing, but instead of using i's and j's or at angle each other, I'm doing this. And the question is, how do you represent v like you do it this way? And the answer is, it's going to be so many of these E1 vectors plus so many of these E2 vectors. Again, provided that the E1 and 2 vectors are not in the same line. In general, what they have to be is they have to set something that's called linearly independent. So v is going to be written as A1, E1, like this. That is, it's so many of these plus so many of these. So I'm deliberately putting these little superscripts here for the case of this, these what are called basis vectors. And this is what's called the contravariant representation. So it works the same way as you're familiar with, but if these things aren't in a straight line, then or aren't at right angles to each other, then some unusual things happen. For example, normally, if you want to find the length of this vector, you square the first component and the second component, right? If you just square a1 and a2, for example, you square a1 and add it to a2, you will not get the norm of b1. That is, you just can't use these numbers in this way if these things are coordinated. In fact, other stuff won't work like this. In other words, the normal thing you're familiar with will not work in these more general settings. And so the question is, how do you recover as much as you can of that? And that's what we're trying to show you here. And the answer is very, very clever. Apparently, this is due to Leviceva. These are some Italian mathematicians who worked on these ideas. They worked shortly after Riemann to sort of generalize Riemann's ideas. And the cleverness is to use a second coordinate system. And you'll see this, by the way, in the study of crystallography and material science, which is another reason why I'm supposed to see this. And that, in those cases, they use the lower subscript. So imagine constructing a new set of basis vectors, which have some specific characteristics. Let me show you what they kind of look like. First of all, this new basis vector, we're going to use subscripts to denote them. And what they're going to be is at right angle. Let me just show you what it looks like. The first one is going to look like this. We call this E1 with a subscript down below. So E1 has the property that if you dot it with this vector here, you're going to get 1, and it's going to be perpendicular to this too. And so the reason we want to do that is we dot E1 with this vector in this notation, then we will recover the kinds of things we're familiar with. So one will be like this. So this E1 vector here is going to be perpendicular to E2, and then the E2 vector is going to be perpendicular to E1. In general, what's going to happen is these what are called covariant vectors are perpendicular to all the other vectors except the one they kind of match with. And the purpose of that is to cover some things. You'll see that in a minute. We call this E2. So we can also write this vector B in terms of that basis. So instead of just having one coordinate system, we're assuming there are two of them that are related. And you'll see the terms reciprocal lattice, covariant basis vectors, all those notations being the same thing. So this is usually written as B1, E1 plus B2, E2. Let's take a moment to stare at that. This is the kind of example I would put on an exam to show you in 2 dimensions to see if you understand this. Okay, now what's going to end up happening is the characteristics of these basis vectors are as follows. We want that E1 with a little subscript on the bottom, but this is called the covariant representation. And so in the covariant representation, it's the subscripts on you use subscripts to represent the coordinates. In the contravariant, you use superscripts. The term contravariant and covariant refer to the fact that if you should change the size of E1 and E2, the contravariant versions, you make these things bigger, these coordinates will become smaller. So they're contra to a change in those basis vectors. So if you don't change the direction, just make them larger, then these things will get, the numbers here will get smaller. It's just the reverse for these other ones. In the case of right angled coordinate systems, those two, the contravariant and covariant systems, are again, they're basically the same thing. And that's why this distinction is not obvious unless you start thinking in a more general sense. You also hear the term dual vector or dual basis for that. Okay? All right, so we stop here and take a little bit of break. Let's come back at 6:05 sharp, and we'll pick this on. Okay. Okay, we're back. Let's go ahead and continue on. Okay, so one of the new really innovative ideas here is that in more generalized situations, we don't just use one coordinate system, but we use two that are related. In the normal scheme of things, when you're studying these kinds of systems, the classical XY systems, these two literally are overlapping one another. So you don't see them as two separate things. And that's why it was hard to discover this the first time. But when you get to the more general situation, you have to imagine there are two coordinate systems that are related. Remember, one of the reasons why people were interested in this was because they want to be able to recover these kinds of features. They want to express everything in terms of a classical dot product. Later on, this was generalized to an inner product. We've seen some examples of that. In your future classes, in the not too distant future, you're going to be using those inner products and these ideas in your quantum mechanics classes. So here's an opportunity to see them in classical context, and some study of this is going to pay off well in those courses, and also course here for the classical applications. So remember that when we did this idea here, that you could take the vector I in the classical case, the orthogonal case, and dot it with B to get the projections. If you represent your vector this way, and you dot it not with the first thing, but with this, but with the covariant vector product, here's what happens. If I dot E with V represented this way, then that's going to be the same as E1, A1, E1 contravariant representation, A2, E2 contravariant representation. And then what happens is these covariant basis vectors have the property that when they're distributed, you get A1, E1 like this, where the subscript and superscripts match this way, plus A2, E1, E2. And only in the case when these two match do you get 1, everything else you get 0. And so it kind of works the same way before. So these covariant vectors will play the same role. It turns out that in the classical cases, they're identical, but here in the general case, they're not. And so it's these qualities that we want to be able to capture. And then it'll turn out that if you want to find the norm of a vector, what you do is you simply dot the following thing. So for example, if I went V dot V, you guys know how to do that. But here, what we want to think about it this way. V1, E1, E2, E2, dotted with E1, E1. And when you dot these together, what you're going to end up with, things that are non-zero, is going to be B1, A1 plus B2, A2. So this is the generalization. You have a subscript, superscript pattern. So I'll go over this a little more with you, but I wanted you to see what the motivation was. This will end up being the length, the square length of the vector. And the reason why the Chitova and Einstein was interested in this kind of stuff is because if you ask the basic question, if you draw a vector like this and use different coordinate systems, what must remain unchanged? And that is the length of the vector. That whether you use regular coordinate systems or skew coordinate systems, the length of the vector would remain the same. If you took the cross product of two vectors, what would remain the same? The area that those two cross span. So in other words, there's certain geometric things that remain unchanged if you change coordinate systems. It is those things that must be physical. And that's what the mathematicians were and physicists were trying to understand. In Einstein's deep application, what he assumed in his postulates, think about it as an axiomatic system, he made two fundamental postulates. One, that the laws of nature were independent of the coordinate system, which kind of makes sense that the laws of nature shouldn't depend upon how you represent it. You're going to truly be universal. And two, that the speed of light was the same in all situations. So if you insist that the speed of light remain constant, everything else has to adjust to make that happen. And that's where you get those exotic kinds of phenomena where you get time contracting and length contracting. It's to cause that to occur. So no matter what you do, no matter every experiment you try, you'll always measure the speed of light to be the same. And this comes out, it was originally suggested by the famous Maxwell equations you're going to learn next semester, electricity and magnetism. There's a tensor there too, the famous Faraday tensor. And when that first came out, people kind of understood that the speed of light should be the same based on those equations. But they thought, well, when we apply this to Newton's laws, it should change a little bit. As they kind of played around with it, they found that if they did that, it didn't make the predictive electromagnetic features that it would have, and most importantly, it didn't match experiments. That was the key thing that brought Einstein's idea to the fore, and these were sort of tools to do that. So let me just show in a very simple example how you would find those contrary and covariant representations, and we'll show you the generalized case, and we'll go to gravitation. I just want to get you to see this key feature. So the kind of equations that these vectors have to satisfy are the following. For example, E1 dot with E1. So a covariant basis vector with a contrary basis vector with the same superscript matching, that always has PD1. Everything else has PD0. So for the two-dimensional case, the one we're going to work on, this is going to be equal to 0. Likewise, E1 dot E2 dot E1, that's got to be 0. E2 dot E2, that's got to be E1. This 1, 0, 0, 1 pattern should remind you of the identity matrix. And in fact, that's going to be the case. So if you had something, for example, E1 being equal to the basis vector 2, 1, which is a superscript of 2, and E2 equal to the basis vector 1, 2. So what I'm thinking about is a vector like this. This is just the vector 2, 1. Another vector like this, 1, 2. The question is, how do we find the corresponding covariant vectors? And the answer basically is to solve this problem right here. If you think about it for a moment, this dot product here requires that the following be true. Now the covariant vectors are written this way, where the contravariant vectors are written this way. So here's where the 2, 1 goes. Here would we write 1, 1, E1, 2. This would be the components of the E1 vector. That's got to be equal to 1. Likewise, I write E1, 1, E1, 2. The other basis vector 1, 2, that's got to be equal to 0. You can also satisfy this equation here. You write E1, 1, E1, I'm sorry, E2, 1. E2, 2. With the first basis vector, which is 2, 1, that's got to give us 0. And I'll show you a shortcut for this in a minute. I just want to demonstrate why it would work. E2, 1, E2, 2. Started with 1, 2. That's got to get you 1. Okay? So here's the shortcut. Create a matrix like this. And you could use this on a quiz, and I'm sorry, baby. And what you do is you write your basis vectors here, 2, 1, 1, 2. And that's got to get you the identity matrix. All you got to do is just find the inverse of this. That's all you have to do. And if you do that, the inverse of this is going to be the thing you need. Because if I multiply both sides by the inverse, now I'll give you this result here. So just remember that it's these quantities here which represent the covariant basis vector. So that's basically just put these numbers here in a column matrix and then find the inverse. And you can put that in mathematical in a second. By the way, you might want to try, they're very easy to do by hand. And you may want to play around with them. I don't just remember. It was, I believe, the second one. So it's 2, 3, and minus 1/3. And for the other one, it's just going to be minus 1/3. It's a symmetric one. Okay? So I encourage you to kind of try it. It's a very easy linear system to solve by numbers. All right? All right, let me show you the one application of this. This will give us the definition of what a tensor is in that sense. Okay? So now let's consider the curvilinear case. I don't know if you guys have seen such coordinates before, but it's a generalization of even the skew symmetric case. It allows us to do the general problem. So let's consider, these are called curvilinear coordinates. Imagine like taking a grid scale here and just kind of warping it. imagine if you drew it on plastic, an x, y, z coordinate system. If I call this, for example, the point x1, x2, and I add a little change, this would be dx1, this would be dx2. I'm going to get this warped triangle. And this is a legitimate coordinate system because if you place this on top of a flat blank sheet of paper, you can assign a pair of numbers to every point. The problem is the triangles are going to be distorted, but something still has to be preserved, the lengths between points. And so we can imagine constructing a little kind of weird triangle like this. This would be ds, and this would be dx1, ds2. So what's going to happen here is that the metric tensor is going to determine what ds is. In fact, ds squared is going to be gij dx1 dx2. Back to ij2. There's a sum here in the Einstein notation. We're picking for you. Right? But the big idea here is you know that if we change coordinate systems, our physics must remain the same. So something has to remain invariant and unchanged. Now, stay with me on this. Imagine you had a second coordinate system overlaid on top of this. And so to every spot, you can name two coordinates. You can have more if you want, which is two of them. And the custom is put a little bar on top of this. So the bar represents a different coordinate system from the unbarred variables. Now, in the same manner, you can go from rectangular to polar coordinates and polar rectangular. There are equations of transformation. For example, if you go to rectangular to polar coordinates, you know, for example, that x squared plus y squared equals r squared, or actually x squared equals side to this. That is, if you know what the rectangular coordinates are, you can plug it into this relationship and give you the polar coordinate. And you know that if you take the inverse tangent of y over x, that's going to give you the angle. So you can go from rectangular to polar, or I can go the other way around. I can go from polar to rectangular. Those are the ones you're probably most familiar with. And these are called equations of transformation. In the same manner, if you have two coordinate systems, there must be equations that transform them from one to the other. So I can imagine the following scenario. If I call x1, x bar 1, that is the first of these coordinates, it's going to be some function of the other two coordinates. This is, by the way, in a two-dimensional space. If there was 3 or 4, we would just keep on adding. So take a moment to see if you're okay with that. All I'm simply saying is that the value of the x1 coordinate is some function, two variables, of the other coordinate system. And it goes both ways. So each coordinate is a function of the other one. Likewise, we can write x bar 2 is some second function of the coordinates. All right? So now let's consider this idea. If we start right here and we change x1 and x2 just a little bit in a differential sense, then the changes in the new coordinate must be proportional to that. So the change in x1 is going to be proportional to the changes in x1 and x2 in the first system. So this implies that d x1 bar, the differential, is going to simply be the partial of f1 with respect to x1 dx1, partial of f1 with respect to x2 dx2. This is what we were studying before. Take a moment to stare at that for a second, see if you're okay with it. That what we're saying is that the changes in the new coordinate system are simply going to be proportional changes in the old coordinate system. In fact, these numbers here just represent a certain fraction of this. And what I'm kind of saying to you is that the differential in this new coordinate system is some linear combination of the differentials in the old coordinate system. Everybody okay with that? Now, if you have a situation where every one of the coordinates, or every one of the quantities change according to this rule, that is, if you have such an object, then that object, the collection of quantities, is referred to as a tensor. So tensor is defined for our purposes of our course as a set of quantities that follow the same behavior as these differential quantities do. So you could write a similar thing for this one. So that we could write, for example, dx bar 2 is going to be the same thing. This going to have a different transformation rule. dx1 plus this partial derivative dx2. Now I can make this a little more compact. This is what you'll see in the literature to describe it. Just take a moment here to stare at that, make sure you guys sort of understand that. So the differentials in the new coordinate system are just simply going to be combinations of the differential in the old coordinate system. If a quantity changes in that way, all the quantities there, then that is a tensor. So vectors change this way, for example, gravitational, electric, magnetic vectors change this way. The metric tensor changes this way. The moment inertia tensor changes this way. And if you do this rule, what ends up happening is if you do the transformation rule, all these things will sort of cancel out, and you'll end up with the same structural formulas in every coordinate system. And that's the key big idea. Just to show you how the way Einstein would work on this, remember that I could use variables subscripts for this, so I could kind of write this in compact notation. I could write dx bar beta equals the partial of alpha dx alpha. This is the kind of way it would be. Let me kind of see if you understand what this notation. Remember that if you have a superscript and a subscript combination, what that means is you're summing over those two variables. So in this case, this dx alpha would be the same as 1 and 2 in this two-dimensional case. This just represents the transformation function, where beta is either 1 and 2 as well. And so any set of quantities that behave like these differentials, that is what a tensor is. That is, it transforms according to this rule. That's what I want you to sort of digest and think about. Okay? So in questions I would ask you, to basically discuss these things. You don't have to be hyper technical about it, but I do want to understand that concept. Okay? So think about that a little bit. All right, let me switch gears here a little bit. I want to talk about classical gravitation, and we'll tie that into what we're talking here. But I need to develop this so I can give you the more modern picture of things. All right. Now, to do this, I need to take a little digression into astronomy. Again, this is just a light touch. I highly recommend that you consider taking astronomy class here in the park, or perhaps other colleges in the future. But you should take it at least one time in your life because it's such a wonderful subject. So let me just kind of mention a few little technical terms here, and I would lightly cover this on exam. And I will put these topics that I want you to zero in on also on the study guide. So those are things I really want you to consider. Some I've mentioned here, and other ones you should be familiar with. So if I could take you out into the middle of an open field, away from everything, just out, out where there's no people, just a clear night sky, and ask you to describe what you see, what you would see is a giant bowl above you, apparently. At least it looks like that. And the name of this thing is called the celestial sphere. So there is really not a sphere there, but you can imagine that there's something up there. And the stars and the moon, the sun appears though they're painted onto the sphere. This entire sphere appears to rotate, carrying those things with it. And this is probably the most common astronomical observation. You've all seen this before, where the sun rises in the east and sets in the west. And the name of that motion carrying out is called diurnal motion. The word diurnal basically means daily. Now, it looks to us, observationally, experimentally, as though the sky is rotating. Of course, we know that's not what's going on. It's the Earth that's rotating. However, there's a very interesting philosophical question. What if the sky really did rotate? What would look different? And the answer is just about nothing. The key is just about. There are obviously subtle changes of some differences, but for the purpose of trying to predict where the sun would be, like for example, you saw the sun rising in the east and I want to see if there is going to be a noon, you could use those motions to make some pretty accurate predictions, which is exactly what infant astronomers did. So they assumed that the ground was still and everything else was spinning around it, because that explained what they saw. That was a theoretical axiomatic system in which they could deduce a lot of things. And it wasn't perfect, but it was actually pretty good. It's just that other observations were inconsistent with that model, and it ultimately had to be updated. And that is the way science progresses. We start with making approximations, and if the theory is pretty good, we kind of use it for a little while until we find something where it does not work. Now, when we do go to the new theory, we've got to explain two things. One, we've got to explain new phenomena we haven't seen before. We've got to be able to explain why the old theories that were working pretty good aren't quite up to the task completely. So in this particular case, though, this is how for most of human history they were thought. So you should have some familiarity with the concept of diurnal motion. It's just the motion of the things across the sky through the Earth's rotation. The most common manifestation of this is the rising of the sun in the east and setting in the west. If you can now go out at night and look at the stars in the sky and look around, you notice again the stars shift in this way too. It's actually, you can see it in real time in a telescope. You actually see the stars drifting in the telescope. In fact, when you go to Professor Sommer's observatory at Mopar College, you get a chance to see some of those things. But what one thing you discover is that there's certain places in the sky where the drift is very, very small or not at all. And near the star we call the North Star, the drift is almost minimal or zero. In fact, there's going to be a specific point. In fact, if you think about this situation, the sun would rise here in the east and set in the west. This diagram here, then you would know generally that way is east, generally that way is west. And if you look to the north, generally, and you spend some time at night, you would discover there's a special point in the sky called the North Celestial Polar NCP. It's a particular place in the sky which the entire sky appears to spin. It's not the North Star, it's a mathematical point. The North Star just is close to it. And if you spend some time looking at it, you can imagine taking a stick and aiming it towards that. And, and then if you hung some strings from that stick, they would just touch the ground, and that would define a line going exactly due north and south. In fact, that's how north and south are defined. So those lines, by the way, are called plumb bob lines, and they're used, of course, by construction engineers to build straight buildings. Except in Italy, the famous Tower of Pisa. That's not quite true. The ground was a little softer in the Tower of Pisa. That kind of changed a little bit. But this is a way in which a north-south line can be constructed. You can then use geometry to find a perfect east-west line. And this is, of course, done in every civilization that ever has some kind of astronomical tradition, which is every civilization. And this explains also why the roads typically in most towns run north and south, except for cities like Burbank or something that where the whole city is rotating. But most roads typically run north, south, east, and west. In flat areas, hilly terrain, of course, is more difficult because of we talked about before. And if you can now imagine going a little, by the way, the angle between the North Celestial Pole and the horizon is actually your latitude. So here in the Southern California area, it's approximately 4 degrees north. If you now construct like an imaginary stick at a right angle for this stick and then sweep it around the sky, it'll define a line in the sky called the celestial equator. You don't have to know all this terminology. I'm just doing it for background, give you some discussion. This line here, by the way, is a projection of the Earth's equator out into space. And it kind of divides the upper half of the sky from the lower half of the sky, just like the equator divides the north half of the planet from the southern half of the planet. If you spend a little more time looking at things up in the sky, what you'll notice is that the stars in the sky, of course, they move together with the entire diurnal motion, but the space in between them, very similar we talked about in the case of points, they remain constant. They call it the fixed stars. But there are these special star-like things that seem to change. The Greeks called these stars wanderers because they would wander from position among the rest of the stars. And the Greek word for wandering is planeta, and the Greek word planet. So the Greeks will look at certain special things in the sky and see them change. And they also see changes in the position of the sun and the moon. In fact, if you watch the position of the sun carefully, say at sunset, you'll discover that there's a line in the sky that kind of runs like this, and the sun shifts against the background stars about 1 degree in the sky. So that motion is called seasonal motion. We're just laying out some of the astronomical evidence we have for things up in the sky. Again, the ancients just thought that these were things moving around us, that we were standing still, everything was moving around. So then I'm going to show you some of the evidence for how we kind of know that that wasn't quite the case. And so the reason why the sun is doing this is not because the sun is actually moving. If you kind of look at a top-down view of things, here's the sun here, here's us. And to sort of exaggerate this a little bit, if this is us on the Earth, you can imagine here's a student looking at, if this is looking down on the Earth, then this would be just at sunset, because here a person is observing midnight. So if you imagine looking at sunset, you've all been to the beach or sometime at some time. You notice that pretty sunset going on here. And of course, you're with your friends, you're talking about the physics of this. That's what's first thing in your mind, of course. But it turns out if you look at the sunset, you can actually see stars if you look carefully. In fact, you can see stars in broad daylight if you know exactly where they look. It's a little hard. It's hard to do, but it's not impossible. And if you kept coming back to the sun at the beach every night, taking a look at this, what you notice is that the stars here will start to shift like this. That is, the angle between that star view and the sun will get smaller. And it's not because the star is moving, it's because the sun apparently changes. And the reason why that's happening, you've got to imagine, if this is you looking at the sunset, the stars are out here someplace. And so you can draw a straight line from you to the sun to the star. And then, of course, the next night, if you did it again, you'd be seeing something like this. Now I'm exaggerating this for effect, but this is what's going on. You can also sense this because if you look straight up at midnight, you will see stars above you. Whereas at midnight here, you're going to see stars above you as well. And so the sky changes from night to night. Remember the classical, oh, by the way, the two other motions to mention, again, you're not going to be tested on this. One's called precession, mutation. There's a couple other smaller ones. Precession is exactly what you've seen before with the gyroscope. So the Earth behaves that way due to the pole of the sun and the moon. They both work on this. And it causes the position of the North South pole to make a wobble every 26,000 years. A mutation we've seen before is that the change in the inclination angle of the body. This takes about 46,000 years. And those cycles, by the way, they sync up. Sometimes they get in step, they get out of step. This creates the ice ages on Earth. But this observation here is a clear indication. It's an explanation for the shifting of the position of the sun. And if you believe in what's called the geocentric model, that means that you're standing still and the sun is going around you. If you believe in what's called the heliocentric model, then you're flying around the sun, and that's what causes these changes. Now, people in the ancient world accepted both as a concept. They chose this because there was no evidence for this. As they said, well, gee, if we're flying around the sun, we agree that you would see this, but I would feel the motion. They said, we notice how fast we're going. They had no evidence for that, so they rejected that until some evidence was accumulated. I want to show you some of the evidence here that pertains to what you want to understand. So one thing that does go around us is the moon. And so if you stand here on the Earth like this, and so here's the moon, here's the sun. One thing you may, of course, look at if you look at the moon, in fact, I think it's this way. Take a look tonight. But you know, when the moon's up in the sky, sometimes it looks like a half, sometimes it looks like it's full. Those are called the phases of the moon. And in this particular configuration, the thing to understand about this is that the sun shines on one side of everything. It shines one side of the moon, one side of the Earth. And so it lights up half the Earth, it lights up half the moon. And we see a portion of that lit half as the moon flies around the Earth. And those are called the phases of the moon. You're probably familiar with that. What you might be less familiar with is that everything does that. If you look at Mars, look at Jupiter, look at Venus, all objects exhibit phases for the exact same reason. The sun lights up everything halfway, but we only see a portion of that lit half. So for example, if you imagine the moon moving like this in this position here, it's going to light up this half, and you see half the lit half, half the dark half, and so it looks like half the moon. Interesting enough, astronomers call that first quarter because the moon has gone a quarter way around its orbit. So I want you to understand that, of course, and when the moon goes behind the Earth, and by the way, it could go directly into the shadow of the Earth, but this orbit is actually inclined. We'll talk a bit about that. So usually the moon is above the Earth or below it by a lot. And so it doesn't go into the shadow. Although if it does go into the shadow, then you get a round shadow, which is actually evidence for the moon. But if it does go above, typically what's going to happen is you'll see the full lit half. That's what we call it full moon, or full phase. Right? Now, what's interesting about this for us is that one of the models for the solar system, which we refer to as the Ptolemaic model, thought of this, this is what was going on. Here's the Earth, here's the sun, and then what was happening is Venus moved around a spot like this. Planet Venus, which you see as a pretty star in the morning sky or noon sky. And by the way, it happens to be up in the morning. So if you're up early over the next couple of weeks, I highly recommend you take a look at it. You're going to get spectacular alignment of planets, in particular Jupiter and Venus, which we know astrology is a bunch of baloney, but typically the astrologers are coming out of the woodwork saying, oh my God, Venus and Jupiter are getting lined up. And it's going to be quite spectacular. And usually that portends in astrological circles, momentous events. But the way they sort of thought of this, you could draw a line between the Earth, center of the circle, and the center of the sun. That Venus would move around like this. And the reason why this is important is because Venus is only found in the early evening or early morning. You never see Venus at midnight. And that's because, the real answer to that is because Venus is orbiting inside the Earth. But if this was true, and this was prevailing wisdom, then Venus would never get behind the sun, and you would never see a full phase of Venus. So think about that for a moment. We see a full phase of the moon because it literally gets behind us, and it's above the Earth as well, so we can see the fully lit up face. But if Venus actually moves in this way, it never gets behind the Earth, behind the sun, and therefore you would never observe it in full phase. Problem was around 1610, Galileo, who invented the first astronomical telescope, he invented the first telescope. He was the first person to have the bright idea to actually look up at the sky with it. Most other people were looking at their neighbors across the street with their friends, or actually they were building for naval purposes. But he was one who looked up at the sky with it to try to see what was up there. And one thing he did was he looked at Venus, and he saw a phase of Venus just like we see the phase of the moon. And he saw a full phase of Venus, which told him that this could not be correct. And this was the smoking gun evidence that had to overthrow the prevailing theory that was prevalent for over 2,000 years. This was what people thought in terms of scientific circles. But it had to be changed because there was evidence that didn't fit the model. And that's how science progresses. It's not that the people who thought this were dumb or anything like that. They went with the evidence that they had. In fact, they thought of all these other ideas too. They just simply rejected it, sadly, for the right reason. They didn't have enough evidence to support that conclusion. Of course, what should have led them to think of more experiments to do it, but these experiments were hard without a telescope. But this led ultimately to the heliocentric hypothesis, what, of course, we know and love today. So it was Galileo who first recognized that, yes, indeed, everything goes around the sun instead of around the Earth. But if everything is going around the sun, if you sort of fast forward a little bit to the time of Newton in the 1660s, and that's when Newton's laws come into development. Remember that if the sun is here and the Earth's going around it, then the Earth is not moving in a straight line. If it's not moving in a straight line, then therefore it must be changing its direction. If it's changing direction, it must be accelerating. If it's accelerating, there must be a force causing that acceleration. Therefore, there must be a force between the Earth and the sun. We'll go over that logic again, and that force, of course, is gravitation. So the existence of gravity, obviously you know about gravity pulling us down here on the Earth, but gravity is a universal characteristic. You could say, well, gee, it's just something strange on Earth, and maybe there's a magnetic field or something. But this is a fundamental thing between any two objects, at least in this classical description. So if the Earth does not travel in a straight line, obviously it must not travel in a straight line, it's orbiting the sun, then it must be changing its direction. If it's changing direction, it's accelerating. Any accelerating object must have a force causing that acceleration. Therefore, there must exist a force between the Earth and the sun. And the next question you would ask here is, what is that force? Now, a little bit before Newton's time, there was another person I just want to mention here by the name of Johannes Kepler and Tycho Brahe. I mentioned Tycho first. So this is roughly around 1600, just a little bit before Galileo's time. The reason I'm mentioning it is because at that time, one of the things that astronomers did was they basically kept accurate records of where the planets are, where everything is. So where's the moon, where's the sun, where's the planet, and then they want to know what are the changes that were going on, so they can make predictions, like eclipses and other kinds of things. So over the centuries, people got better and better at this, using ordinary sighting sticks. Tycho Brahe actually was probably had the best collection for over 20 years. He looked at the sky every night he could. He kept very accurate records of what he saw, the equivalent of an Excel spreadsheet. Unfortunately, he wasn't a very good mathematician, so he didn't know how to take those numbers and process them basically to try to find patterns in them. But he had a person who was working with, by the name of Kepler, to kind of, I'm short circuiting, this is a very long story, but the key thing is that Tycho's observations eventually made available to Kepler, who sifted through them and processed them to create a new axiomatic system for astronomy. And these are the famous laws of Kepler. Let me just mention them quickly. They're not going to be tested on them. The first one is called the law of ellipses. I do want you to know them, but you don't be tested on them. The law of ellipses just simply says that the planets move in elliptical paths. And that was a fundamental break with classical theory, because in classical argument, the planets have to move in circles or combination of circles. So Kepler's making a big change here. It took him 10 years to come up with that. We're going to actually show you if we can prove this using Newton's laws. The third one is the equal area law. And what that law basically says, in the short version, I want you to know, is that if you, by the way, the sun in this ellipse is not at the center, it's off to one side. As the planets orbit in this elliptical pattern, if they're far away from the sun, they're going to move slowly. If they're close to the sun, they're going to move quickly. And you could draw some triangles like this, which represent the area they sort of sweep out in equal times. Then the equal area says that in any given period of time, they're going to sweep out the same area, which is equivalent to saying that they have to go fast when they're close, far away, slow when they're far away. And that is equivalent, interestingly enough, to the conservation of angular momentum. If you look at the sun and the planet, that system comprises a two-particle system with a certain amount of momentum. So what he's really backing into is the conservation of angular momentum. He just didn't know it. Those concepts hadn't been developed at the time. And the last one is the famous p squared equals a cube law. It says that if you measure this distance usually by the variable a, in astronomical units, the averages from the Earth and the sun, then that value in the orbital period will be related by this relationship. The beauty of this relationship is that if you know one of them, you can compute the other. Now, it turns out you can't measure the distance very easily, but you can measure the period. So therefore, once you know the period, you can compute the distance, and therefore you can compute how far things are away. Let me just give you a very simple example. If you had like a new asteroid you had just discovered, and the orbital period was 8 years, then you could plug that into this formula, and you'd end up with 8 squared, let's say cubed. Now this is 64, and the cube of 64 is 4. That implies that a is equal to 4. So therefore, the orbital size of that asteroid would be 4 astronomical units. So Kepler came up with these laws empirically. He just simply looked at a lot of instances of planets. Well, he didn't do it, people did. They just processed it, and they came up with these patterns. And this represented a new marked change in our understanding of the solar system. Newton was not just looking at motions of planets, but all motion. And it turns out these rules, or these axiomatic assumptions, can be actually deduced as theorems starting with Newton's laws. We're going to actually prove something for you. I just want you to know the law in itself. So that makes Newton's laws much more comprehensive. Einstein took it a step further. So there are things that Newton's laws can't explain, but my laws can. One of the beautiful ones was if you look at the orbit of Mercury very carefully, so here's the sun here, Mercury does something like this. It's called the precession of Mercury's orbit. It doesn't make a closed loop. It has this kind of flower petal shape. And for centuries, astronomers had seen this, but they could not explain it. Interestingly enough, their explanation was there was another planet inside Mercury's orbit. It went by the name of Vulcan. No kidding. Okay? And then that planet disturbed the orbit. And they looked real carefully for it. They never found it. And it turns out that Einstein was able to explain with his theory this phenomenon in the same way that Galileo was able to explain the difference between the geocentric and heliocentric hypothesis. So part of it is we're going through this discussion, you can see the classical explanation of progression of science in this manner. Okay? So let me stop here. When we come back on Tuesday, we'll talk about the Cavendish experiment and some of the classical results of that. Okay, so if you have questions, hang out. If not, have a good